Hey there, welcome back to Short Text 331. And today we're going to finalize the discussion of linear operators. Of course, there's a lot more to say about linear operators. These are only our short takes. But to complete our discussion in this channel, we're going to talk about three theorems. And our first theorem on linear operators is as follows. If the kernel of A, our operator A, is just a zero vector, and remember that linear operators always map the zero vector onto the zero vector no matter what. You can always prove that by linearity the zero is always mapped onto zero, but if that's the only vector that's mapped onto zero, then A is 1 to 1. That is to say, is injective. That is to say that for a given result, there's only one vector that it's coming from in the domain vector space. And if that's true, if you have 1 to 1, then you have the inverse operator as a true operator that exists. Now, as I was saying, note that A applied to 0 is always 0. That's always true by linearity. And so if A is injective, then it must be that the kernel of A is 0. So the converse property is also true. That is to say, if you already know that A is 1 to 1 in some way, then it must be that the kernel is also 0. So these properties of the kernel being just 0, having just that trivial kernel with only a 0 vector, and your operator being 1 to 1 really go hand in hand. They're equivalent. Now, let's do the proof then. We assume that the kernel is just a 0 vector, and let's assume that A is not injective. So what that means is that there are two different vectors that could give you the same answer. That's what we mean by an operator being not injective. There's at least two. In fact, it could be more, but there's at least two vectors that give you the same result when you apply A. Now, by linearity, we can add these two results and combine the left-hand sides into A applied to V1 minus V2. We can do this by linearity. And on the right-hand side, we would get W minus W, and so that's 0. But if that's true, then that means that V1 minus V2 is in the kernel of A. But the kernel of A is only a 0 vector, so it must be that V1 minus V2 is 0. That's to say that V1 is equal to V2. So again, that tells us that the operator A has to be injective. So we assume that if V1, V2 were different, we allowed for that possibility, and we end up with a contradiction. That is that V1 has to be equal to V2 if the kernel of A is 0. And so then that proves our statement that if the kernel of A is just a 0 vector, then A has to be an injective operator. That is to say, is 1 to 1. Again, that means that if you have a given result called W, then that can only come from one V1. It cannot come from two different vectors, V1 and V2. We just proved then that if you assume that these two vectors end up being the same vector. And so that means that A is injective. So here's our second theorem. The inverse of a linear operator is also a linear operator. This may be obvious to some of you, maybe not. It's an interesting proof, and it goes like this. So by definition, if we assume that A applied to a vector X gives us a vector Y, then it means that A inverse applied to Y gives us X. That's the definition of the inverse, right? So A maps X to Y, and so by definition, then the inverse maps Y to X. And of course, we're assuming here that the inverse exists and there are no issues of any sort. We're just saying we're going to prove that if that inverse mapping exists, then it's a linear mapping. And we start with the simplest step to prove linearity of A inverse. We see that if we apply A to a constant times X, then the constant goes right through the operator. That's the probability of linearity of A. And then we get C times A applied to X, and that's C times Y, because we assume that AX is equal to Y. And so A applied to C times X is equal to C times Y. But then this means that the inverse operator applied to C times Y is C times X. By this equation here, the inverse applied to C times Y has to be this input here, that's C times X, and so this must be true. And by this identity here, that AX is equal to Y, we can replace X by A inverse times Y. And so the effect of this chain of identities here is simply that A inverse applied to C times Y is C times A inverse applied to Y. So the C goes right through the operator. And so the operator A inverse then is at least linear in that sense. If you have a constant multiplied by your vector, then that constant goes right through your operator, as you see here. Now, what about the sum of two vectors? Well, we know that A applied to the sum of two vectors is the sum of the two results of applying A to the first vector plus A applied to the second vector. And let's assume that this result, AV1, is W1, and AV2, we call it W2. And so A inverse applied to W1 is V1, A inverse applied to W2 is V2. We know that. And what about the sum? Well, if we apply A inverse to the sum of W1 plus W2 here, then it must be that that's equal to V1 plus V2 by assumption here. But in turn, we can write V1 as V2 as I just said. V1 and V2 are themselves, for example, V1 is A inverse applied to W1, and V2 is A inverse applied to W2. And so what this accomplished then is that A inverse applied to the sum is the same as the sum of A inverse applied to each vector independently. And that then proves the other property that we need for linearity. We need the property of the sum and the property of the product by a constant. And that proves then that A inverse, if it exists, is also going to be a linear operator. So in other words, the inverse operator inherits the linearity properties of A. If you find this video helpful so far, please like and subscribe. If you're looking for a tutor in physics or math, in English or in Spanish, I'm happy to help you. You can contact me at shorttakes331@gmail.com, or you can leave a comment in the comment section below and I'll get back to you. Our third theorem today is a bit of a different kind of theorem, but it's related to the other two. The statement is that the columns of an invertible matrix form a linearly independent set. And I'll remind you what we mean by linear independence. But the one thing you need to pay attention at this point is that we're going to write our matrix A as columns. And we're going to call these columns vectors, A1, A2, A3, and so on. So imagine that you have columns of numbers like that, and that form our matrix. So in other words, I form my matrix by assembling all these vectors one next to the other from A1 to AN. And them being linearly independent means that if I form a linear combination of them and I set it equal to 0, then the only way to get that to be 0 is if all the constants in the linear combination vanish. And we're going to use that. Now suppose that AX is equal to 0 for some X. Okay? This is always possible because at least we have X equal to 0. We know that. Now, if A is invertible, then it must be that X equal to 0 is the only solution. And we know that because one way to think about it is that it must be that the kernel of A is just 0. We know that. And so then 0 is the only solution to this. Or you can think about it this way. If A inverse exists, then I can put the inverse on the other side of the equation. And I'm applying A inverse to the vector O. There should be a vector here, a vector arrow. And so A inverse applied to this vector 0 then gives me 0. And so X equal to 0 is the only solution. So if A is invertible, then X equal to 0 is the only solution. But we notice that A applied to X actually takes this form. If you recall, if you go back to our lecture on matrix vector multiplication, you will find that there's this way of thinking about matrix vector multiplication that tells you that you can write the product of a matrix by a vector as this sum, where each of the components of your vector X enter multiplying the columns of the matrix A. So we have our first term here, X1 coming from the first component of X, applied to the column A1 plus the second entry in X applied multiplied by the second column of A, and so on and so forth until you get to the last component of X multiplying the last column of A. And so this is a linear combination, clearly, of the columns of A. And if that is equal to 0, to the 0 vector, and the only way to get that is that X is equal to 0 because A is invertible, and the only the only element in the kernel of A is just 0, then it must be that this implies that the only way to get this equal to 0 is that all the X's are 0. And if the only possible solution is that all the X's are 0, then that's the definition of linear independence. And so immediately this this tells us that if A is invertible, then the columns of A form a linearly independent set. And the converse is also true. If the columns are linearly independent, then we see by this definition that the only way to make this vanish is that all the X's are 0 and there's nothing else. And if that's true, then that implies that the kernel of A is only 0, because that's what it means to have that characterizes the elements of the kernel. The elements of the kernel are the elements X such that AX is equal to 0. Well, if the only way to make this combination AX equal to 0 is that all the X's vanish, then kernel of A is just the 0 vector. And we know then that that means that A is invertible, because we know that the kernel of A being just a zero vector means that A is one-to-one, and a one-to-one function, be it linear or not, if it's one-to-one, then it's invertible. That is to say, if we know where we're going with a function and there's only one a way to get there to the result from the domain, then that means that we have an invertible function. That is, once given the result, you know where you're coming from, and you can define the inverse. And so we're in a safe place, then the inverse exists. That's all I have for you today. We only, in terms of theorems, we have an example left that I want to show you in terms of how this all works out. Suppose that you have, for this last theorem, suppose you have a matrix M, then that's 3 by 3, and it's given by this, and 1, 2, 3, 3, 1, 4, 2, minus 1, 1. And so the columns then would be M1, M2, and M3. And what you see in this matrix, and I built this matrix like this on purpose, is that M3 is equal to M1 plus M2. Let's check it out. So 3 is 1 plus 2, 4 is 3 plus 1, and 1 is 2 minus 1. And so indeed, the last column is a linear combination of the other two columns, is M1 plus M2. And so these three vectors are not linearly independent. Okay, so if these three vectors are not linearly independent, let's see what happens. Well, applying the matrix M to X, to a given vector X with components x1, x2, x3, then we have x1 times column 1, x2 times column 2, and x3 times column 3. And suppose we force that to be equal to 0. We say, well, let's see which x's we can find that give us a 0 vector. Well, it turns out that that can be accomplished if x1 is equal to x2 is equal to minus x3. And that's easy to see because, and that could be, for example, x1 equals to x2 equals to 1 and x3 equals to minus 1. That satisfies this equation. And that's easy to see because suppose we set that to this condition. Well, let me make x1 equals to minus x3 and x2 equals to minus x3. And so if that's true, I can put minus x3 here, minus x3 here. I leave that x3 here, and I can rewrite this equation here as minus x3 times this combination. But this combination is 0 because we see that M3 is M1 plus M2. So no matter what x3 is, no matter what I put for x3, I get 0 as a result. And so this tells us that the kernel is not just a 0 vector. Okay, so when you have a situation like this, that the columns are not linearly independent, then the kernel becomes non-trivial. Otherwise, the only solution would have to be 0, 0, 0, and clearly that's not true here. I could put x3 to minus 1, I could put it to x3 to minus 2, to minus 7, to whatever I want, and as long as I satisfy this condition, then m times x, this non-trivial x, is going to be 0, and that non-trivial x will be in the kernel. And if that's true, then the matrix M is also not going to be invertible. And so this matrix in particular then is clearly not invertible because of all this chain of logical identities and implications that we discussed before with the previous theorem. Once again, if you enjoyed this video, I encourage you to like and subscribe. If you're looking for a tutor in physics or math, in English or in Spanish, you can contact me at shorttext331@gmail.com, or you can leave a message in the comment section below, and I'll see you next time.